So far, we've been looking at simple shadows that fall on a flat ground plane. This made it rather easy to find their shadows using the pole method. Now we're going to take it a step further with different kinds of terrain that go up and down. Here we have a simple pole that's right beside an isometric hole. Now we're going to use the angle down and the ground angle to find where this shadow goes and how it is affected by this hole. I'm doing it in isometric so you can see the concepts more clearly without all the complexity of perspective. First, we'll have a ground angle. And then we would have the angle down come over the top, and where it struck, this ground angle would be the end of the shadow. But we have to deal with the hole. We take the ground angle and what hits the edge of the hole, kind of like the box we did. The angle has to go down. Then it continues over to here, where behind this lip it would go back up to here and continue on. The shadow you would see in the hole would be right along there. Now the hole has a shadow itself, so you could use this flagpole to find its shadow. And like in the box, we know it's going to go between that top corner and where it hits the bottom. Therefore, you won't see this part of the shadow. Your shadow will end up looking like this. If the angle down were different, the shadow might even end in the bottom of the hole. If the angle down was like this, it would stop here at the bottom of the hole. Now we'll go back to our pole and we'll have the shadow go over something. Here we have a rectangle that's in the way of the shadow. First we'll decide on our ground angle and we'll make it like this. Again, we think about it, it wasn't there, that's the way the ground angle would go. But if you think about it hitting it, it's going to hit it, it's going to go straight up, then it'll return to the ground angle, go across, it would come down and back and resume its normal angle. Now where the shadow stops, again depends upon what the angle down is. If the angle down is this, the shadow is going to stop on the other side of the box right there. If the angle is less than that, it could stop right there. Or it even could stop going up the side. We've been dealing with right angles, which is easier. The slants just take a little more thinking. Again, we have our ground angle, which would be like that if the object was not there. But it's going to hit a slant, so it's not going to go straight up. We have to figure out how it goes up this surface. Well, the way we do that is, we know where it hits here. If we can calculate where it would be here, we can draw a line between them. Now the way we do that is, we find out where the back side of this is, because it is a right angle. Then we see where the shadow would hit this right angle. And we just come up to the top. We then know that this angle would be from this point to this point. Like that. Dropping in the angle down will tell us where the shadow would stop. Slight angle like this, it would stop past the object. Again, if it was a steeper angle, you could even have it stop on the object. If the angle is slanted on both sides, you can drop in what would be like one of our poles here from the highest point down to find where the edge would be in the bottom, so that you then could find the peak point up there. I have zoomed in on the curved surface so you could see more clearly the construction lines we have to make. You have to imagine we still have a pole off here to the left, and it's casting a shadow off to the right. This is where the shadow would be if the curved surface was not there. Now we're going to figure out where the shadow would be on this curved surface. The way we're going to do this is we're going to have to find some points like we did when we calculated the shadow of a circle. Then we're going to have to connect the points to find the curve that represents the shadow going over this curved surface. We're starting out with our poles. We have a selection of poles here in the middle and then equal distance on the way to the edges. We don't need one over here because it's around the back side. What we do is we pretend that this curved surface stops at this pole and goes straight down. So we find where the back edge would be of this flat surface and where the shadow would hit it. Where it hits it, we come up to where the top of this pole would be, and that's one of our shadow points. Moving to the next pole, we do the same thing. We find from the bottom of the pole where the edge would be if it was flat on the back. We go back from the top of our pole where the shadow would intersect the bottom. We go up to the top and find the second point. Third pole, same thing. New bottom line, new top line, shadow hitting, intersection, up to the top of where it would be on the curved surface. Pole number 4, and the last pole. Now it looks like there's a lot more room here, and I'd like to have another dot. Well, the beauty of this system is, whenever you need another dot, you can drop in another pole. And now that I have all my dots, I can start where the shadow hits the side and then move along the surface as it loops around and back. And here we have the shadow on the curved surface, which represents the shadow that would go clear through it if this surface wasn't here. Once again, using poles, you can locate where the shadow would be at any given point, then connect the points and find the shadow. Now we have found shadows that go into holes, over geometric structures, up slants, and over curved surfaces using the pole method and a ground angle and an angle down.